We start the afternoon session with Mariya Ishteva from Leuven talking on decoupling multivariate functions using tensors.
This is the longest polynomials that I could fit on my slide. So these are two polynomials. They have two variables, x1 and x2, and degree 3. So hopefully you can imagine if I increase the number of variables. Do you hear me? Yeah?
Is it okay? No mic?
Yeah. So if we have more unknowns, not only x1, x2, but let's say 5 of them, or if we increase the degree of the polynomial, hopefully you can imagine that the polynomials will get very, very long. And if we do both at the same time, let's say 5 variables and degree 5, then this polynomial will go to the next building. And they are actually perfectly nice. We just cannot fit them on the slide. So my presentation will be about fitting them on the slide without losing any information. And what I would like to do is for all the polynomials, not only for the long or for the short ones, to get to an alternative representation. So for these ones here that we can see, this would be the representation. So what do we have? We have two matrices here on the left and on the right, and they give linear transformations. So basically we allow the two unknowns to be mixed together, and then we send them through a polynomial function, and then allow the results of this, in this case, two polynomial functions to be mixed again. So somehow it looks more complicated because now we have more elements in our polynomials than the original ones. But I would like to claim that this is not the case. So this is, for me, much simpler representation. First of all, we have some linear transformations. So we know how to deal with linear stuff, so we are happy about it. And here in the middle, we have polynomials, yes, but they are univariate polynomials. So these are polynomials in only one variable, whereas the original ones have 2 or 5 or even more variables. So basically, in this representation, we can very easily increase the degree of the polynomial or the number of variables without increasing too much the number of parameters that we have. So for this one, yeah, maybe it's more or less the same order, but for much longer polynomials, with this representation, we'll have a safe of a lot of variables. And then moreover, so the number of parameters is one thing, of course, interesting, but here we hope to get some interpretation. So the fact that we have univariate polynomials instead of multivariate polynomials gives us some hope to understand the underlying structure of the polynomials better. So here this arrow says, okay, I can go from one representation to the other. And the way I did this, which is the main question, is how do we do this? Yeah, I started, of course, from this representation and made this one to show you the slide. But for this talk, we want to do it the other way around. So we want to start with something that we don't understand, potentially with many parameters, and we want to bring it in a form which we can understand with less parameters. Sounds like magic, but that's why we have tensors. So spoiler alert, there are some tensors coming up. And this representation also looks a little bit like the singular value decomposition that was mentioned this morning. So there we decompose a matrix again with some two matrices and something that is diagonal in the middle. So it's kind of a generalization of the singular value decomposition if you're familiar with it. Okay, good. And I'm not doing this alone. I've been working with a lot of people for the last many years. And most of them are engineers. So I spent many years convincing engineers that it's interesting to look into the mathematics of a problem. And today the challenge is to talk to mathematicians and tell them, okay, we can actually do some engineering stuff with the mathematics that you're developing. So challenge accepted. This will be the story today. So for engineers, this would be theory, but for you, it's now history. A very small section about how we came up to this problem, which is not true, but it's convincing enough. Then a section about computations and a big section about applications. So we go back to the 1770, where the varying problem was formulated. So what is the varying problem? It says that every natural number can be represented as a sum of at most 4 squares, 9 cubes, or 19 fourth powers. So for example, if we take the number 30, we need at most 4 squares to represent it. Yeah, in this case, it's 3, 5 to the power of 2, plus 2 to the power of 2, plus 1 to the power of 2. So it's true. This is not a proof, of course, but it's true. Then we can also use cubes. We need at most 9 cubes. So for 30, we can represent it with 4. And we need at most 19 fourth powers. Here we need quite a lot of them, but it's still less than 19 or equal. So this problem was formulated and people were wondering, yeah, is it always possible to do this? And what are the numbers? And the answer was given many years old. So this is like 250 years ago. So this is a very old problem. And a little bit more than 100 years, people found the solution of this problem. And they said, yes, for every power that we choose, we can find a number S, so that every natural number can be represented as a sum of powers to this K. And the number of powers that we need is smaller or equal to S. Okay, so far so good. But of course, people don't stay still. They say, okay, this one is solved, and we introduce new problems. And this is how we come to the varying problem for homogeneous polynomial that we have seen actually today and yesterday, maybe under a different day. So what is the story here? Instead of numbers, we'll now decompose functions or polynomials. So we start with a multivariate polynomial of a certain degree, homogeneous polynomial, and we want to represent it as sum of powers. So it's a homogeneous polynomial of degree d, so the powers that we take will be, of course, d. What do we allow? A certain number of terms, r, because it will relate to a rank to a certain tensor. And then here we allow linear combinations of the initial variables. So there is also a scaling factor here, which will make everything real, because otherwise we'll have to deal with negative powers and maybe we'll need to go to complex numbers. So this is the general formulation, and it's related to the symmetric tensor decomposition that we have heard a few times this week already. And here is a toy example. Suppose we have a small term here, 4 times x1, x2. It doesn't look like a sum at all. It's actually a product of variables, but still we can represent it in this form with 2 terms. This is x1 plus x2 squared and x1 minus x2 squared. And the question is it always possible? Yes, it is always possible. How do we do it? That's a more difficult question. But it has to do with tensor decompositions. Okay. So there is actually a lot of work around this problem about homogeneous polynomials and decomposing in this particular form. But we decided to go to a different problem. It's a variation actually. And we said, okay, we don't want to limit ourselves to homogeneous polynomials. We would like to do this for all the polynomials. And also sometimes we want to decompose polynomials together. So not just one and decompose it, another one decompose it. If we know that they are related, we want to jointly decompose them. Basically, we want to use the same combinations of variables to represent both polynomials at the same time. And now we are back to our example. So these are the polynomials. This is how we want to represent them. Is it always possible? Yes, it is. Can we compute it? Well, we'll find out. So the number of branches that we need here, it also relates to the rank of a certain tensor. Okay, good. So now I have to start giving notation to things so that we can do a little bit of math, not much. So I'll call my general function many parameters and potentially different functions like here, f. So this f of x. So this will be my V transpose matrix that makes combinations of the inputs. So these are the variables, or sometimes we call them inputs. They go through this matrix, and then they go through these functions, which I'll call G. So G, we have all these that are in the middle, and then we send everything through another linear transformation. So we have to multiply with another matrix. So the matrix U is this one.
You're going to allow U and V to be rectangular in general?
We can allow them to be rectangular is easy. Yeah, I mean easy. Square is easier. Depends which side rectangular. Of course, if we have
Square would be very rare.
Square would be rare, okay. Rectangular, one is easier than the other. So we have here, let's say 10 variables and 10 functions. If we have less than 10, it's an easier problem. If we have more than 10, up to certain level, we can still do it. Actually, we'll see it's a tensor problem. It has to do with how to compute the symmetric tensor decomposition of a symmetric tensor, but then the generalization of it. So we have the same issues. If the rank is small enough, let's say up to the dimensions or a little bit more, then it's okay. If we go further, then we start getting into problems. Okay. So for this one, of course, it's an artificial example. I started from here, I went there, so it's very easy to find it back. Very easy, maybe something that also has been mentioned, but not explicitly. What do we hope to get? Suppose I start from this representation. This is the underlying representation, but this is what I can measure, or this is what is given to me, and I want to find this compact representation back. What can I hope to find? Because we can see that there is a scaling factor that can jump a little bit through the 3 layers. So there is something with scaling that we cannot recover. And also we cannot recover a permutation of this middle functions. So we wouldn't know which one is the first one, which one is the second one. And it's the same actually with tensor decomposition. Sometimes people call it rank decomposition or canonical polyadic decomposition. So the decomposition where you decompose a tensor into rank 1 terms. What do you hope to retrieve are the rank 1 components, but the vectors you can only get up to scaling, and the components you can also permute. So there is something with scaling and permutation that we cannot retrieve, but we would be happy. So we'll be happy if we find a version of this where the scaling and permutation, only the scaling and permutation is different from the original one. Okay, so we allow some factors. Let's say if I multiply this time 2 and this one times 2 and the whole matrix here by 1/2, I get the same result, and there is nothing we can do about it. It's not a question of computing it, but it's intrinsic to the problem.
But these polynomials are fixed.
Yes, they are given. So this is given. This is what we're looking for.
Maybe variables.
No, nothing is given here. It's only the structure, only the lines.
Yes, in the worrying problem, they are powers.
They are powers. Yeah, in the varying problem, it will be something like this. Not even, because they maybe have to be the same.
You can always homogenize them.
But in our case, they're polynomials. Any polynomials. Univariate. Okay, we can have different variations at the end. I even claim that it doesn't have to be polynomials. It can be another basis because of the way we solve the problem. But we'll get to that point. So at the moment, they are univariate polynomials, not necessarily homogeneous. This is what we are after. We are given multivariate non-homogeneous polynomials. We want a representation. We are looking for the entries of this matrix. We are looking for the coefficients. And we are also looking for the entries here. So again, spoiler alert. So if the tensor decompositions, they do their trick because of some uniqueness properties. We don't even have to give the degree of these polynomials because we would get the zeros for free. Okay, there is free lunch. Okay, good. Other questions until here?
Does taking non-homogeneous polynomial make this problem more general, or is it the same through homogenization?
It might be that it's the same through homogenization. The reason why we do it like this is because of the engineers' friends that we have. They had non-homogeneous polynomials. They gave us, okay, do something with it because we are getting crazy. Yes, that's how it happens.
Tell us what the engineers do.
I will.
Okay, you will.
Yes.
Okay.
First, I'll tell you what, let's say, computer scientists do, and they're actually computing things. So first, I'll tell you how we compute it, and then I'll tell you what the engineers do with it. Because it sounded like a logical presentation for mathematicians. The engineers want it the other way around. They want first to see that it's doing something, and then they want to see if there is something like an explanation, intuition behind it. And the next level of proving things is sometimes left behind. But I also leave it behind here because I've been working with engineers for a long time. Okay, so now we want to compute it. So this is the formulation that we have. Given is a function f that we know. We know the function description. We are looking for the U matrix, the V matrix, and some coefficients in the G polynomials. And also maybe not new to you because we saw partial derivatives today and yesterday. We can decide to take a first order approach. So we can decide to look at this function in some points and look for first order, which is like a linearization of the function in different points. And how do we do this? We do this by taking derivatives. And which is your favorite rule for taking derivatives? The chain rule, yes. This is the chain. So we'll use the chain rule. So what does the chain rule say? The chain rule says that if we take a derivative of a function of another function, we should take the derivative of the outer function, but we should also take the derivative of the inner function. So what do we have here? We have this U, which does not depend on X. It's just a constant matrix. So basically it can go in front, right? It's a constant. Then we'll take derivatives of the G, partial derivatives with respect to the variables. And then we'll take the derivative of V transpose X. So we can look at it for a while and imagine how it would result.
So you're starting with some kind of a promise that you can have a decomposition of a certain size.
Size.
If you're making some assumption that U is a matrix of a certain size and V is a matrix of a certain size, then they must have promised you that there'll be a decomposition of that nature.
Okay, so the function has a number of variables. This is given.
Yes.
It has also it's a vector function. So it has.
I'm talking about the variables in the middle.
Yes. Okay. So these are already one of the dimensions of U and one of the dimensions.
Sure.
And then we have something in the middle. But at the moment, for the derivation, we don't need to know what it is. For the computation itself, this will be the rank of a certain tensor.
Right.
But at the moment, it's just R.
But when you're doing your computation, are you making assumptions, or are you going to look for the rank at the same time as attempting to do the decomposition?
I think it will be clear in 2 minutes.
Okay.
Yeah, and if it's not at the
I'll
end
ask
of the
again.
slide, and then you ask again. Okay, good. Okay, so but we decided to go for the chain rule because we looked at local information about this function. It's at the moment polynomials. It's very well behaved. Let's say. So how will the partial derivatives look like? So we have a number of variables and a number of functions. So the partial derivatives is actually a matrix. Right? It's a matrix of partial derivatives. So we have the partial derivative of every function with respect to every variable. So this is this matrix. We'll call it Jacobian matrix. And now, as we said, we'll apply the chain rule. It says, okay, u is a constant. It can just go in front. Then we take derivatives of the internal functions. And then the chain rule says we can take derivative of what is here inside with respect to x. So this is v transpose. So there is something strange happened here, that when we took derivatives, this matrix in the middle became diagonal. So why is this? Because we take derivatives of every function with respect to every variable. But we said the functions in the middle, the g functions, they're univariate. So they will create a non-zero entry only on the diagonal. If we take a derivative of g1 with respect to the second variable, it will be 0. It doesn't contain the second variable. If we take the derivative of g1 with respect to the third variable, it will also be 0 because it doesn't contain it. So this is the first interesting fact, that here in the middle, we get a diagonal matrix. So only on the diagonal we have no zeros. Everywhere else, there are zeros. And there is one more interesting fact. And this is that we have here a matrix U, here a matrix V transpose, but they do not depend on X. So they are constant. So we have a decomposition of this Jacobian for a given X, which is a matrix, a diagonal matrix times another matrix. We know F. This matrix we can construct. In fact, we can construct as many matrices as we like, because for every X, we get a different matrix. So basically, we evaluate the derivatives, the partial derivatives in different points. For every point, we get a matrix. So we have a bunch of matrices, and all of them we can decompose as U, some diagonal matrix, and V transpose. Do you know what it is? Yeah? It looks like SVD, but then the tensor version of it. Another guess? Yeah, so we can collect these matrices, we can stack them behind each other, we create a tensor. And what do we get? We get a tensor, like with all the matrices that we make. These are the ones that we know. And we know that all of them we can represent as a U times some diagonal, which is different every time, and the same matrix V or V transpose, depends on the notation, but let's say a matrix and a matrix, these are fixed. And this is a diagonal tensor. And this is exactly the decomposition of a tensor in rank 1 terms. We can call it canonical polyadic decomposition. As here, we can call it a rank decomposition.
So can you ensure that there exists a simultaneous diagonalization?
Well, basically, yeah, we have a tensor, and this is the canonical polyadic decomposition of this tensor.
But the Jacobian matrices, they commute. Why should there be a common diagonalization for all of them?
Because of the chain rule. So the chain rule says every matrix I can decompose as U times the derivative of G, which is a diagonal, because the G's are univariate functions. So all the other things are zeros.
So
times V
you,
transpose.
you sample the matrices.
We
So for
sample, yes,
each Jacobian matrix is at a given point.
yes.
But then U and V depends on point.
No, that's the beauty of it. They don't.
And why?
Why?
Sorry for asking.
No, thank you for asking. So we are after this decomposition. So this and this, they do not depend on
But so
the
you
point.
assume them to exist.
We know that they exist
Why?
because we can decompose every tensor in rank 1 terms. The only thing that we don't know, he's gone, is the rank of this tensor. Let's say we are looking, at the moment we are looking for the, polyadic decomposition. We would prefer to have the canonical one. We would like it to be minimal. But somehow, we'll come back to this. Sometimes we don't. Sometimes we want that we have more terms, but maybe with some properties, with some structure. So then we can allow it to have more terms. I just gave your answer. No, I was saying we were decomposing matrices as a product of a matrix, a diagonal matrix and a third matrix, and the first and the last one are always the same. And this is equivalent to taking all the matrices in a tensor and decomposing this tensor in rank 1 terms.
No, my question was about R. Are you
Yes,
making
R is the rank of this tensor.
Right, but so you're making the assumption you have an upper bound on the right from your decomposition.
Well, at the moment, this is for any R. When we compute it, of course, we need to know what the rank is. And we know that it's a difficult problem. And that's why we count on you to make this right, to get the tensor decomposition for us.
And even if you have R correct, if somebody doesn't like you picks F, the decomposition may not be unique in modulo the things you mentioned. It may fail grammatically also.
Okay, picking the right points is an issue if you really want to be mean. But if you just take random points, if you take enough, we don't have to take a minimal number of points. We can take as many points as we like.
A mean person picks F.
F. At the moment, they're polynomials.
No, but
So, multivariate polynomials.
Yeah, but some bad person picks F.
How
then,
bad?
Then you will not have anything resembling unique decomposition.
Okay, then we'll.
The set of bad F is small, so if you pick, even if you have a promise of R and you pick F at random, you're probably okay. But there are ones that will cause failure.
I guess your engineer friends have good Fs.
Yeah, my engineer friends are not that mean. They just have real. Don't have good R's. R is difficult to find. I mean, there is no explanation. We don't know how to pick R. But of course, for engineers, it's good enough if you say you try 1, you try 2, you try 3, and once you're happy, then you're happy. And they are very happy with this. But I'm not going to solve an unsolvable problem. How do we find the rank of a tensor? Because we all know that it's a difficult problem. So somehow here, when we do this, we rely on the new generation now, tensor people, to get new algorithms for computing this decomposition, because we actually need it.
Sorry for asking. I'm not an expert in tensors. That's why my questions may seem to be really trivial. But what is a tensor? It's a three-dimensional tensor.
For me, it's a three-dimensional matrix, if you want.
Okay.
Yeah. So it's basically a bunch of matrices that we want to decompose together. Yeah. It's just that they come from the partial derivative of the function with respect to all the variables, and then we take it in different points. So for every point, we get a matrix, and we like to put them behind each other to create a three-dimensional structure, because then we can rely on the polyadic decomposition, for which there are some solution, for which there are enough solutions in a friendly environment. And a lot of software. So go to any mathematical software, Python, Julia, MATLAB, then you can find this decomposition there.
So here you made a strong assumption that you have this G1 of Z1 and G2 of Z2.
Yes, this is the model that we are after, this one. And it relates somehow to the intuitively, not a proof, to the singular value decomposition where we have matrices. Okay, they're also orthogonal, but here they don't have to be. Doesn't matter matrices, and then something diagonal in the middle. So this is our version of diagonal, which says we only take univariate polynomials. And when we do that, we get the nice property that this matrix gets diagonal. And then we can rely on theory that is behind the rank 1 decomposition of tensors.
And I think you mentioned you get univariate polynomials homogeneous of certain degree. That's what you put there.
Yeah, not necessarily homogeneous, but yes, it can be any polynomial because we just take derivatives. We don't care if it's homogeneous or non-homogeneous. We can do both.
Okay.
It's the same for us.
So how do the engineers do this? They start with some small r and some low degree for the g's, and then they just keep going up until they.
No, the truth is, they go to some software and they say, "Give me the rank estimation."
Wait, so it's like the software has to go through some kind of algorithm.
Yeah.
And is the software is varying. My question is this: is the software both varying the degree of the g's and r, or is it sort of fixing the degree of the g's and varying r? Or
well, in theory, you only need to vary r.
I agree. That's why I asked the question.
Because if you have the right r, the theory says you have a unique decomposition up to scaling and permutation, and you get all the zeros. You can put degree 10. It will give 0 for all the coefficients that are higher than 3 if the polynomial is of degree 3. So in theory, you only need to vary r, and the rest is for free. If you can compute this. Yeah. And we know that mathematically, we cannot compute it, but at the same time, for engineers, they can compute it. Because they're not trying to break it. They're using some real data, measurements, and in the real measurements, you don't get very, very crazy effects. So basically, it's computable, and they're also happy with approximations. So in mathematics, we care a lot about computing everything exact, but engineers, they're happy if they get 0.1% error. So that's actually the most important slide. Are there more questions about this? Yeah.
Are the Jacobians are in different points, or are they representing for the other derivative?
So this is a formula that says take the derivative with respect to all the variables. At the moment, they are variables, and the formula is true for every point. And then, but it's a formula. It depends on x. So once we fix x, then we get a matrix with numbers. For another x, we have another matrix with different numbers. So basically for each, think of it as this is a matrix of functions. But then when we evaluate them, we get a matrix of numbers. So for every point, it's a matrix. Yes?
I would agree that the f's, number of f's goes up, we have to sample more. Yeah. Benefit for composition, how much it will max.
For sure, if we have more variables or more functions, it might be that we need to sample more. In theory, we need to sample as much as the rank somehow. Is it true what I'm saying? I need to think about it, but it has to do with the rank of the tensor. And if we increase the degree, it might be that the tensor has a higher rank, and then we need to sample more. But in theory, like if we don't try to break it. Even 2 sampling points will be enough because we can use. Okay, you're trying to break it. That's why. Yeah, it's the eigenvalue decomposition that we saw this morning. So it's basically 2 slices if everything is exact. Huh? Sorry?
Exact or approximate, you can compute the.
In theory, if everything is exact, then 2 slices will be enough. Huh? Numerically, it's nicer to have more to take care of some errors.
No, but you need more slices because you have degrees which of the G which are not 1. Sorry, if you need to go to degree 10, you will need at least 11. That's right.
Yeah, at the moment we are just fitting. So we'll see in some examples we are not fitting the coefficients. We are fitting the function. So the degree of the polynomial, it doesn't relate like this to our problem. It only relates to the rank of the tensor, which can make us need more sampling points. But we are not fitting coefficients. This is what we want at the end, coefficients. But at the moment, we have like a discretized function. And what we'll get is a discretized function of the derivative.
But maybe you can show us this.
Yes, yeah. So this is the algorithm. Basically, we compute the Jacobians in different sampling points. We compute the rank 1 decomposition of the tensor, and we already get for free U and V. And now we have 2 options for the G. Either we take this matrix, which is a discretized version of the derivative, and then integrate it, or we say, okay, once we have U and V and everything, so once we have the function and this, fitting the coefficients is a linear problem. It's solving a big system of linear equations. So we could also do that. So we can say, okay, now we want to compute G. Either we integrate H or we solve a linear system of equations to get the coefficients of G.
So which is what is H?
H, yeah, because here we have to do with derivatives. We have U, V, and here we have evaluations of the derivatives. These are the H. So it's not the G, but it's the derivative of G.
Okay.
So H is the derivative of G.
Okay, okay.
And from the decomposition, we get the derivative of G, but we would like to have G. And the options that we have is integrate, that's one option, or solve a system of equations for the coefficients.
But for U and V, you don't need to pass the tensor, you just need one sample.
We need the decomposition. So U and V we get from this. So these columns make the U matrix. These rows, they make the V matrix. And the other ones,
yeah,
we can decide to use them or not to use them.
But so you need to have as many HI as the degree plus 1 of the G.
The degree is not directly involved here.
I mean, otherwise you cannot construct the G. You get only sampling of this function. Derivative.
If we have, okay, we can take it offline. But if we have everything, if we have the function, if we have these coefficients already and this one already, then we can refit the whole thing. We are only looking for coefficients, and this is a linear problem because these coefficients, they don't appear squared or to the power of 3 or to the
But it must have a problem.
You have to have the number of equations and the number of unknowns.
Yeah.
So to match up.
Yes, the number of coefficients depends on the degree of polynomial you put inside. How many coefficients you need? That depends.
Well, it can go different ways. That's why I'm saying there are 2 options. So either we take H and we integrate.
What do you mean integrate? You reconstruct from the values.
Well, you can if it's a nice smooth function, you can fit a function and then integrate it, and then you get the integral
Of samples.
from samples.
So it's approximate.
Yes, everything is approximate. Only the theory is exact. Everything you put in a computer is an approximation. Even real numbers, you put it in a computer, it's 10 to the power of minus 16.
But you can still like that.
I don't know if how quantum computers work, but at the moment, you put a real number that is not a natural number or not a friendly number. And okay, it seems like a different discussion. Okay. Okay, I have the feeling you want to know more about the application than of the variations, but here just to mention. So I said somewhere we started the motivation from the varying problem where we decompose one polynomial, but we now decompose many of them. And my natural reaction would be to think, yeah, decomposing more polynomials is more difficult than decomposing one. But in this case, it's not true, because if we only have one function, if we take the derivatives, it's not a matrix, it's a vector. And if we evaluate it in different points, it's not a tensor, it's a matrix. And once we go back to the matrix world, we lose uniqueness property of the decomposition, and then we're in trouble. So actually, for this setting, scalar function, so only one function decomposing, is more difficult than decomposing multiple functions.
Or you just take higher order derivatives.
Yes. So we can go to higher order derivatives, but then we lose also some information. So every time we take derivative, we lose some of the coefficients. You lose the constants, then here you could lose the linear terms. Okay. So another thing that can happen is we said about uniqueness. If the rank is reasonable, up to the dimensions or maybe a little bit more, then we get exact decomposition. But in some extreme cases, the rank can get larger so that the decomposition in its free form is not unique anymore. Or like our friends, the engineers, like to work with noise, and then we don't have exact decompositions anymore. So in both cases, we need some modification of the problem. And there are a few things that we could do. We could parameterize, so we could actually go and look for the coefficients, but then the problems become a little bit more difficult. The optimization problem. Or we could also look at joint decomposition. So we can combine information of the Jacobian and then the second order derivative, the Hessian, or the zeroth order information, the function itself. And in this way, we can actually extend the class of functions that are decomposable in this way. Something else interesting, because we said the internal functions are univariate, and this might seem like a strong assumption, or it might be undesirable in some applications. So we can also combine them per 2 or per 3 or per some group, small groups, if we know that this is important for the applications that we have. But then, of course, we cannot go to the rank 1 decomposition. Then we need a decomposition in low rank terms. But also this has already been developed in the tensor community, and it's called block term decomposition. It will solve this problem for us. And then we could also decide to go for multiple layers. And I don't know if I have time, but I have an example about this. And there are also tensor decomposition that relate to this version of the problem. For example, the Paratuk 2 or Z decomposition. Okay, so do I have 5 minutes or how
Yes,
much?
more than 5.
Okay, so how we actually started working on this was from engineering point of view, from system identification, where the engineers try to model everything around us. So everything is a model, it has input and output. So these are measurements. You measure something at the input of the system and the output of the system. And the easier systems are linear systems. And the easiest that we will discuss today are linear dynamic systems. It means that they have a little bit of memory, a little bit like in the Fibonacci example that we have. It remembers a bit about the past. But there are also many non-linearities that they want to fit. And it's very difficult to combine the dynamics of the memory of the system with the non-linearity of the system. That's why they decided to work with blocks. So this is one of the approaches. It's called block term block system identification. So you separate, and this is also very true for many applications, that in some places of your system it's non-linear, in others it's dynamic. So you can basically separate the blocks, or if you're not happy with this, you can add more blocks. And there is a theory that says if you add blocks in parallel, even actually without this part, that you have some kind of universal approximator. You can approximate every system sufficiently well with such a structure. And what our colleagues were very good at was to estimate these dynamic parts. So there are some filters with some coefficients, and they could do this, but they got stuck with some non-linearity, which was static, so without a memory, just a non-linear function, which they wanted to split through the different branches. And this is actually how we started working on this problem. So they asked her to separate this function. And once we can do this, we can put the linear matrices to the linear blocks on the left and on the right. And then they get the structure that they want, that they can control afterwards. So this was one of the applications. Another one also came from the system identification. So I don't know if you have heard about impulse response. Who has heard about impulse response? A little bit? Yeah. So for the ones that haven't, suppose I want to know about the acoustic of this room. In theory, what I need to do is to clap once and to measure the signal that comes from this clap. So this is the impulse response. And now if I have an input, somebody talking in the room, I can combine it with a convolution, with some operation, and I know how this person will sound in this room. So only from the single clap, I can know about the whole signal. But this is again for simple system, for linear systems. If we go to nonlinear, then we also have a way to describe them, but these are the Volterra kernels. So instead of the impulse response, we have a generalization of them, which are kernels. They are not vectors anymore. They are matrices, third order tensor, fourth order tensor, and so on. Depends on the non-linearity. And they are readily in tensor formats, so they already have multiple dimensions, and there are methods that try to decompose this as it is to get the parameters from there. What we did was something a little bit different. We thought of it as polynomials. So basically, you get the coefficients of your polynomials from the kernels, and then the variables are the inputs at different points. Okay, and what we could see is this. This was the structure they were after. A, B, C, and D are the linear blocks that they could estimate in a different story, but now we wanted to do it without their help. So we are looking for the coefficients of A, B, C, and D, but we are also looking for the internal functions G. And through the Volterra kernel, we could link it to the same representation that I've been talking for the last hour, but with some structure. So we get the coefficients of these filters in a very structured way. So it's a block topless matrix. And also the functions that we have here, the univariate functions, they are different versions of them. So here we have two versions, here we also have two versions. So we have it multiple times. The only problem was that here we only had one input, and somehow we didn't want to go to the second order information. We decided to create a second input, second output, just by taking one more input of the system. So the system basically takes a number of inputs and gets one output. If I start here, or maybe here, and add one more, then I get the next output. So basically, by just including one more input at the beginning, I can create my second output. So now it is in the form that we like, a number of inputs, a number of outputs. This is the structure that we are after. And we have different options. We know that there is a structure, we would like to impose it, but imposing it comes with a lot of time and effort. So we decided just to try and see what happens. So here is an example that we made. It's a simulated data. So this is the V matrix, the W matrix, and then we took some polynomials. And so the mathematics side of our brain said, okay, don't even try this because we have collinear columns. So this column is the same as this one, and this one is collinear with this one. And if you have heard about Kruskal rank, I think I need to speed up, you know that this is very bad news. If we have collinear columns, then the Kruskal rank of this matrix is very low, and it means that we cannot hope for uniqueness. The theory says that it's very unlikely that we have uniqueness. It doesn't say that it's not going to happen, but it says something like, don't try this. But we did anyway, because we had the engineering side of us and said, okay, we'll try it and see what's the worst that can happen. And this is what happened. So we got, starting from this is the one that we recovered. And then the engineering side said, okay, this is not at all what we were after. We have to give up indeed. But then the mathematics side says, okay, but let's look at it a little bit closer. And then we see, okay, we actually find these columns. We also find these ones. So what about the black ones? They don't look the same, but maybe if we rescale them, they will. And we rescaled them, and this is what we got. It still doesn't look exactly, but we can still match them. So the red column is actually this one, and the orange is this one. And of course, to convince engineers, we also added noise. So the data was not exact to start from. And once we showed them this, they said, oh, this is exactly what we wanted. Because we found the coefficients. We didn't find the full matrix. So if we go here back, we didn't find the full matrix, but we were only after the coefficients. We don't care about the whole matrix. We care about A0, A1, and A2. And these are the ones that we could retrieve up to scaling and permutation. So this is what happened with W, and the same thing happened with V. We see that there is some permutation because here I put only the first and the third column, whereas initially they were the second and the fourth. So maybe just the next slide. So this is about the matrices, and the part about the function that was also in the question is like, what happens now with the functions? How do they look like? Because we know that it's not unique. We knew mathematically it's very, very, very unlikely that it's unique. So we cannot get the functions, but we see that we get the coefficients of the filters anyway. So what happens with the functions is this. These are the original functions that we put, G1 3 times and G2 3 times. These are the original derivatives from these functions. So this is a G1 and this is G2. And these are the ones that we got. Indeed, there is something going on here and here and here and here, but we don't care because we did find the ones that we wanted. So the rest is mixed together. So it's not unique. Some of the columns got mixed together, but enough columns got correct up to scaling and permutations, and they are also enough to extract all the parameters. So actually we can match the second one with this one. We can match this one with this one, as was the case for these two matrices, and also for the other. So the same effect we see here, and this is actually enough. We see that it's enough to recognize the function that is there. So here you can choose to integrate, you can choose to fit and integrate, or you can choose to go to your original problem and fit the coefficients as you like. But from this shape, you can actually see that it was retrieved. Yes, indeed, there was some rubbish on the side, but we don't care because we didn't want everything. We just wanted the information. And this is the story about system identification. I'll skip the part about neural network because there we also found some links. And to tell you that if it's one thing that you want to remember from this presentation is that if you see very, very long polynomials, think about decomposing in some structured form. And if you don't try to break it too much, it will work. So this is the main message. If you want to remember 3 things, is also remember that this is a tensor problem, has to do with the tensor rank decomposition. So with all the consequences from there. It is always possible in theory, if you take the rank large enough, it is also possible for non-polynomials because the method is based on derivatives. So as long as we can take derivatives, it's actually true for functions that are non-differentiable in a number of points, just don't take these points. And then the last one is that it has a lot of application. We started from system identification, we moved a little bit to neural networks, and now we see that even with the newest technology there, the Kolmogorov-Arnold networks, there are also some links with this approach.
Thank you very much. You have time for a quick question?
So back on the slide where you said you have the few good ones and you just threw away the bad ones, how did you know that those were, I mean, I know you had the answer, but in practice, how would you say, okay, I have these 6, those 2 are good and the rest are bad?
Well, in this setting, you can expect trouble because of the collinearity. Yeah. So once you, but also in the answer, you can see the collinearity, and this, you should not trust these 2 columns. The green ones you cannot trust; they are mixed together. The blue ones are also mixed together.
Okay. So you go for the ones which are not.
So you go for the ones that are not dependent on the others. That's the engineering approach of things. Yeah, you want to find the answer, you don't want to find everything.
Yes, Bernard?
So in the joint diagonalization, you do a direct eigen computation, or you do some iterative improvement?
We don't have any contribution in computing the tensor decomposition.
Which tool do you use?
Well, we come from Leuven, so we use TensorLab, which is the MATLAB. Which function? I think we tried with so the CPD. We also use structured data fusion, so it's a way to combine the first order information and second order, but it has more computational issues. For us, just the pure, I'm sorry to say, but the pure alternating least squares works the best.
Should not be sorry. Alternate least square is great.
Yeah, there are a lot more advanced algorithms that for sure have their applications, but if you just take a problem with some real data, which is a little bit disturbed, which nobody tried to break on purpose, then just the simplest technology, the simplest algorithm.
You get the points, they are not very well computed.
Well, first we added noise, so our data was not exact. Yeah. So it relates to, because if you go to engineers and say, I have some algorithms that work in the exact case, please use it, they'll say, I'm not even going to try because I never have exact data, and I know if I don't have exact data, most of the things, they just break. Show me something that works with noise, and the best thing that, in my opinion, you can do is just to add a little bit noise and say, okay, if you add a little bit noise, you get approximately what you want. Of course, if you add a lot of noise, then things can go wrong, but this is something
So
that they agree.
What you got is with noise, it looks like it's 10 minus 3 disturbed. Like
yeah, so this is with, let's say, 1% noise. What is
1%. I see 3 digits. Some digits.
Yeah, but the noise is on the output, it's not on the matrix.
You compute the noise is very strange.
Yes, because these are the ones that are mixed together. So these are the ones that, so you have the green ones, they are together mixed. The blue ones are also together mixed. And this is something that you can see here. With this form, these are the greens and the blue ones, and they're mixed together, you cannot trust them. But the ones that are the orange and red, so here it says, this was actually, I didn't put the full matrix, but it's the first and the third column that were the good ones. So, and they correspond to the second and the fifth column of the original one. So if we go look at the second and fifth, you can match them with the first and the third that we recovered.
So as an engineer, I was told never differentiate noise, but that's what you're doing.
Differentiate noise.
It's differentiate.
No.
Then you get something very messy.
No, we didn't. We just use the data, the noisy version of the data, and these are the results that we get from our tensor decomposition. And from there, now we can decide, because we know what's going on. There's some non-uniqueness, but it's not on all the columns. It's on some of the columns. So we should not use that because it's not noise. We know exactly what.
Map. It's the perturbed map. Then you amplify the
No,
out.
but she's assuming she has polynomials, and she's differentiating polynomials that are unknown. She's not differentiating the data.
Okay. Okay.
This is actually something
You
that we
do that
want to do in the
differentiate.
next to start with real data without the function description and to skip the function
You do
of.
symbolically. You do symbolic
Yes,
differentiation.
we can.
Okay.
Yeah. But the next step would be to start from data, not fit the function, but go exactly to the representation because this is actually what they need. So at the moment, what they do is they take the data, they first fit the function, they give us the function, then we do the decomposition and give it back. But ideally, we want to skip the fitting part as well.
But yes, so
Maybe we take it offline.
Okay.
Okay, thank you again.